I'm delighted to be here. I'm going to be talking about two different topics, both machine learning for systems and systems for machine learning. Given the conference title, I couldn't pick, so I'm going to pick both. And I'm going to be presenting work that is done in some cases jointly by myself and others. In some cases, I just think the work is cool and it was done at Google, and so I have a few slides from collections of people who have done interesting things in these two different areas. So I think the key questions for this community are, how can we apply learning in more systems to make them better and more efficient? That's sort of one aspirational thing. And then also, how can we build better and more efficient learning systems to enable us to train and use larger and more effective models in more places as sort of learning becomes something as a main paradigm of computer science and computing generally. So Rich Sutton in 2019 wrote this fairly nice, not too long essay about the bitter lesson, which I think you should all go read, but I'll quote one piece of it. One thing that should be learned from the bitter lesson is the great power of general purpose methods, of methods that continue to scale with increased computation, even as the available computation becomes very great. The two methods that seem to scale arbitrarily in this way are search and learning. So I think that's a good general lesson. As we get more efficient machine learning hardware and have more computational available to us in all the different places we might want to make decisions, we can actually start to apply learning and use learning to make better decisions through this kind of lesson that we should all take heed of. Okay, so the first part, I'm going to focus on learning for systems. I've said for a long time that traditional systems, operating systems, compilers, memory allocators, storage systems, they don't really make that much use of machine learning today, although that's starting to change. But they're loaded with heuristics that are kind of approximations of policies that you might want to do when those are really very approximate things. Like think about cache replacement. LRU is a very weak approximation of what you would really want, which is to throw out the least useful thing in your cache. And if you have a learning-based system, you can actually often learn more effectively what things you should throw out of your cache. And I think that's a good kind of specific example of all kinds of learning we should be doing in lots of places. So this is, I'm going to show a couple of slides from a talk I gave in 2018 at the NeurIPS ML for Systems workshop. I said there's a bunch of opportunities in lots of these different areas of systems. How do you do register allocation or instruction scheduling in compilers, or networking, all the things that a networking stack has about, policies of when to increase TCP window sizes or decrease them. Those things could be learned. Operating systems, like which process to schedule next, kind of is often got a fairly simple heuristic in it. Could be done better. And similarly, ASIC design was the one I mentioned in 2018. I'll talk a bit more about that later. I said the key challenges were, how do you integrate machine learning into the guts of traditional systems code? I'll talk about a system called Smart Choices that actually we've developed at Google that makes this a bit easier. And how do you make machine learning work well in sort of challenging performance environments? Often you need to make very fine-grained decisions in computer systems. What process to schedule next is not something you want to run your 10 billion parameter neural net on. You want to make a pretty lightweight thing. And then there's a bunch of questions around interpretability, understandability, safety, reliability, and security. Okay, so the good news is there's considerable progress on some of these topics. And so I'm going to kind of outline a few specific instances of trends that exhibit some of these trends. So one is learned compiler choices, not heuristic-driven choices. And I'll highlight an example from some work that we've been doing on our XLA compiler. So in a compiler, the goal of a compiler is to transform programs in a high-level language to low-level representation and then optimize it for performance through heuristics. And then an auto-tuner can help you, the compiler, find better optimization decisions by actually trying lots of different ways of mapping code onto the actual system, and then search the space of configurations and select the best configuration. So we have a system called XTAT, which is an XLA TPU auto-tuner, where you essentially have a bunch of graph level optimizations on the left here that you want to be able to do. Layout assignment of how should you lay out sort of complex multi-dimensional tensors in memory, How should you fuse operators in order to sort of, should you do them one at a time, or should you try to fuse them so that you bring them in from memory, do multiple operations in sequence, and then push the combined result back out to memory? How should you tile various computations to make most effective use of the matrix unit or the vector unit in these systems? And so there's a code optimizer, and then there's a learned policy. So in the yellow are the learned policies that we learn with machine learning models, and then the blue are the optimizations that are tuned by these policies. So here's an example of operator fusion. The naive thing would be to do each of these operations sequentially, push the results back out to memory, and then fetch the results back from memory in order to do the next thing. Instead, you can actually fuse them. So you do an add and a reshape, or an add and a copy simultaneously with one pass over the data, and then push the results of that back out to memory, and then do the next operation. Or layout assignment, the exact ordering of dimensions and the strides in which you're going to do them is another thing you can make decisions on that can be, actually quite big differences in performance. And then you actually can get, quite a lot of speed up combined if the actual speed up is the sum of all these things generally across many, many different workloads at Google, and it delivers a 5 to 25% speed up on sort of important production models by this automated tuning and learned heuristic choices, rather than sort of handwritten heuristic choices on top of the already sort of heavily optimized production compiler. So that's pretty nice. There's been some other work on learned object lifetime predictions to improve allocation policies. So, one of the things you have in a C-style allocator is you allocate some memory, and you need to decide where you're going to put that in the allocator. And one of the things you might like to do is group together objects with similar lifetimes so they all end up on a page where all the objects in the page kind of die at roughly the same time, and then you can free that page back up to the operating system for use for some other things. But if there are any objects left on the page, then the application has to hold on to that page for longer, and that increases memory fragmentation, increases memory pressure in the overall system. And so, the lifetime you'd like to be able to predict, the object size at allocation time, and so you want to be able to make a prediction of what the lifetime is so that you can assign it to the right place. And this is especially important if you're using very large pages, because then, even a very teeny object allocated in your 2 megabyte page keeps 2 megabytes of memory alive, which is not so great. Here's an example of that. In page 2, we have just a handful of objects of it actually active, but we've wasted a lot of memory there. So it turns out you can actually just kind of use the call stack as a input to a machine learning model, where you can now make a prediction based on the call stack. Often if you look one level up in the call stack, that's not actually that predictive of the object lifetime. But if you look 10 levels up, that exact call path is often very predictive of, is that going to be a very short-lived object or a very long-lived object? And so you can essentially just tokenize the call stack, feed it into a sequence model, and make a prediction of the object lifetime. And maybe you just have a few buckets of object lifetime, treat them as natural language, train an LSTM neural network on these call stacks, and make predictions. And so the caching mechanism is you now have 3 lifetime classes, short, medium, and long lifetimes. And you add at the allocation site, you get a hash of the stack. You look up on the cache. If you've already decided, is this sort of stack going to give you, if you've already sort of made that prediction, you don't have to run the model again. You can just look up in the cache. So that's actually quite fast. But if you miss in the cache, then you have to sort of walk the stack, identify the tokens in the stack, and run the more complex model to then predict the lifetime, and then you put it in the cache. So next time you allocate an object with that exact stack, you now hit in the cache. And otherwise, you run the model, and you can periodically discard this cache in case the program behavior changes over phases or whatever. So the same call stack may not necessarily exhibit exactly the same behavior over time, and then you can sort of recompute it, and you make a prediction. And there's a different allocation site So you group these objects with similar lifetimes in the same pages, less than 10 milliseconds, less than 100, and less than a second. And then some of these objects die, they get deallocated. And then what you'd like is for all the objects in a 10 millisecond page to actually have died within 10 milliseconds. But if that hasn't happened, then you say, oh, well, we made a mistake. Let's change the prediction for these call stacks and maybe move this page into the 100 millisecond group and move it up one lifetime class. And then you sort of adaptively kind of adjust your lifetime predictions in the model based on the actual exhibited behavior. And this actually gives a 19 to 78% reduction in fragmentation, depending on the program you look at, which is kind of nice. And is not super complicated. It's sort of one small model that you run in the allocator, and you have a little cache of those decisions. Okay, so Smart Choices is sort of lower level software to make it easy to integrate these kinds of learned choices into lots and lots of places in your system and application code. And the API is basically consists of a few different things. One is context type, which is kind of like the input to the model of all the relevant features you think might be important for making the kind of prediction you're gonna make. And then the ARM is kind of the set of actions you can pick. And this is from the Bandit literature, but you can actually use many different kinds of models. You could use small neural nets in here as well. And then you have some code where you call choose, the Smart Choices choose operation, which chooses makes a choice based on the context. So you have some input features available, and then you make a choice, and that gives you a handle. And then you can eventually decide how good was that decision. And that might happen, very close proximity in the same process, or it might happen much, much later. You might decide to show something in a UI, and the user just clicks on this thing, and that was good or bad, and you get some sense of that in maybe a completely different distributed system process, but you can sort of join that feedback together. And then using that handle, you can give feedback to the system. And that will then sort of close the loop and give feedback to the original context choice and then the choice that was made. And so the actual implementation, you have choose and give feedback, and then you have the Smart Choices service. And as I said, that can, choose can be quite fast. In many cases, you can choose modeling approaches that make choices in microseconds. That runs in the process. Sometimes give feedback can happen very quickly, as I said, but sometimes that happens much later, minutes later in the downstream system. And this Smart Choices service part can either be something linked into the same process, and you use local decision making to adjust a model that is specific to that process, or it could be a part of a larger distributed system where you give feedback operations collected in logs, and this system then runs and trains models and then pushes new updated models out to all the systems that are using that model, so that their choose calls are now reflect the kind of online state of feedback that all the other systems have been collecting, choosing, and giving feedback on. Here's an example of Smart Choices in our YouTube cache eviction policy, and there's a paper in NSDI 2023 that talks about this, where essentially you want to decide which candidate is the best one to throw away from your cache. I mentioned LRU caching. Really, you'd like to look at a bunch of features about each YouTube video, what country is the user in, what country or what language is the video in, how new is the video. You can imagine a lot of things that might influence how likely it is some other user is going to watch this video in the same data set, and want to stream it from the same data center as the one where it currently resides. But it's actually hard to write handwritten heuristics that incorporate all that information. So learning is the right way to do this. And it turns out you can actually incorporate a bunch of those nice features that are sort of seem conceptually related, but hard to figure out how to hand incorporate them and get pretty nice gains. So this actually reduced the per byte miss rate, which is what you actually hear about on YouTube, by 9.1% when it was rolled out in the YouTube system with a fairly modest CPU overhead of 1.8%. So that's pretty nice. Okay. You may have noticed the trend that people are building interesting machine learning accelerators to speed up machine learning computations. And the reason that trend is important is more computational power actually improves the quality of the models we're able to train. And so it's really, transforming the kinds of computations we want to run. If you thought back 15 years, we traditionally were thinking about how do we improve the performance of general purpose CPUs for twisty, multi-threaded C and C++ code. Now what we actually care about a lot is how do we run kind of dense linear algebra computations in interesting ways with very low bit precisions and so on. So we've actually been focused on this problem for quite a while at Google. And the reason is machine learning optimized hardware is much more efficient. You can actually get factors of when the first TPU v1 came out compared to CPUs and GPUs at the time, it was 30 to 80x more efficient for inference. And subsequent generations of TPUs have focused on both training and inference. And this enables us to have larger scale models with lower economic and energy costs. And so here's a few examples of the TPU family. We're actually on our 6th generation of TPU, which was just announced at Google I/O 2 days ago, without very much specifics. So I only have the first 5 here. The first generation was just really a single PCI card with a single chip that only did int8 operations, no floating point, and it was optimized for inference. Subsequent generations, V2, V3, and V4, as well as V5 and 6, actually focus on both training and inference and are really designed to be integrated into whole systems and connect together many of these chips in order to build a training system or an inference system that's larger than one chip. So as an aside, ISCA recently celebrated, the main computer architecture conference recently celebrated its 50th anniversary. And they asked authors of some influential papers to write retrospectives, which is kind of nice because sometimes you get to hear about what was the backstory about why people were interested in this particular problem. And one of them was the original TPU v1 paper in ISCA 2017. Somewhat proudly, it's the #2 most cited ISCA paper in the 50-year history of ISCA, which is pretty nice. But this is sort of the backstory, and I encourage you to go read it on that site. Really, it came out of an observation that we were going to want a lot more inference capacity than we had in our data centers, and we were going to need to actually double the number of CPUs if we were going to use CPU-based inference. And so I managed to convince a bunch of people in our hardware team to think about actually building special purpose hardware. And that's what we ended up building with TPU v1. I convinced Norm Juppy, who was the lead at the time, by noting that every time we try deep learning on something new, it works. And these are the pods that these systems are configured into. And the scale of pods has been going up generation over generation. So the V4 pod is 1.1 exaflops, 4,096 chips. Liquid cooling was added in the V3 pods, but not the V2. And the V5 pods are even larger. They're 8,960 chips with quite a lot of floating point and integer capability, 4.1 exaflops in one of these large pods. And this sort of like many rows of racks of machines in a data center. So that keep that mental image in your mind when you're thinking about some of the large scale training jobs I'll talk about in a moment. I'll take a brief detour and talk about energy usage and CO2 emissions of ML. How many of you have heard about this kind of work or thought about it? Okay, some of you. Okay, great. So there's lots of attention to this, which is why many of you have probably raised your hands. And there's lots of dramatic headlines. Unfortunately, there's a lot of misinformation in this area. And I think it's really important to actually use realistic information and correct information that's actually measured to make decisions about and inform what we should be doing. And it's an important topic. It's critical to use this actual data so that we focus on the right things. So as an example of information that is fairly widely spread in this space. There was a paper in 2019 that attempted to estimate the CO2 emissions of a Google paper that did a neural architecture search to find a model called the evolved transformer. And it arrived at a quite flawed estimate of 284 tons of CO2 emissions for this neural architecture search. And unlike other data in that paper, that paper actually did a really nice job of measuring a bunch of different models on actual hardware and actually measuring the wattage that was consumed. But for this particular measurement, they didn't actually measure it. And then they incorrectly estimated it and in a couple of different ways. So first, they modeled a P100, not the TPU v2 where this computation was actually run. And they assumed a US average data center, not a Google data center. And so the actual search was 5x lower in carbon emissions due to this. But they also then misread the evolved transformer paper and thought that it was using full-scale models to do the neural architecture search, not very teeny models. And so that actually made a 19x mistake, and those compound to be 88x off. And they also misunderstood that neural architecture search is a one-time cost, not something you do every time you train a language model. And that generated fairly dramatic headlines. You may have seen some of these headlines. The particular one that sticks in people's minds is training a language model of this scale emits as much carbon as 5 cars in their lifetime. But fortunately, if you look at things with correct data, it's not so dire, which is good. It's good to use real data. So first, the actual one-time evolved transformer neural architecture search on TPU v2 hardware generated 3.2 tons of CO2 emissions, not 284 tons, 88x less. The reason they were actually running this neural architecture search was to find a more efficient version of a drop-in replacement for a transformer model. So they found an evolved transformer which had the same, actually better accuracy than the original transformer by sort of fiddling with the order of operands in which things fed into the intention layer and so on. And that actually uses 16 to 25% less energy than the main transformer model, and it's open source for everyone to use. So actually, the neural architecture search actually more than repays itself by all the people who are now getting benefit from more efficient usage. And if you actually train an NLP model of the scale examined in that paper using the discovered evolved transformer on ML efficient hardware in a Google data center, takes 120 TPU v2 hours, costs you $40, and generates 2.4 kilograms of CO2, not 284 tons, which is 118,000 times less. So I think the general lesson is this is a super important area. We care deeply about machine learning efficiency as a community and energy consumption and CO2 emissions, but it's really good to make sure that we're using real measured data on the things that we're sort of considering. So, and these two papers linked here actually have a few more details of a bunch of actual measurements of different machine learning models that are larger scale than the ones looked at there. Okay, learning for chip design. I mentioned that we want to be able to design chips quickly or more efficiently. And learning is one way that we can speed up the chip design process and also come up with better chip designs. So we'd like to be able to improve the design quality, but also reduce the time to design chips so that we can deploy more efficient chips more quickly with less human effort. And currently designing a new chip is pretty time consuming. It requires dozens to hundreds of person years of effort and lots of different kinds of specialized expertise in the chip design team. People who focus on verification, people who focus on, physical layout, people who focus on, high-level computer architecture and so on. So if you look at what if designing a custom chip took a few people a few weeks, right? This would be pretty amazing. I'm not saying we can do this today, but I think if you focus on the different sub-problems I'm going to highlight in a moment, there's a chance for certain kinds of chips. I think we could actually get to this point. And that would require solving a few different kinds of problems. One, this is kind of the main chip design flow. You could do architecture exploration and then synthesis and verification and placement and routing. And we've been doing work in all of these different areas. Here's a few representative publications. I'll talk about the first and the last one, and I'll talk about the last one first. And I will not talk about the middle two, but those are also interesting. Okay, so in 2021, we published a Nature paper on how to use reinforcement learning to do placement and routing, high-level placement in chip designs. And there's the paper. I'm one of the co-authors. And this is roughly how this approach works. You have a bunch of things. You have macros, which are typically, pieces of SRAM or other things that are very regularized pieces. And those are you're not going to change the layout of things within that. So you place those as a large blob in some part of the chip. And then the other things are standard cells, which is logic, and that can be moved around a bit. So what we do is we actually cluster those standard cells so that we can now have fewer things to deal with. And then we place both the macros and the standard cells on the chip surface and do that sequentially for all the different components of a piece in an IP block. And then at the end, we can get a reward function, a reward signal. And in our case, we use something that incorporates both wire length, congestion, and density of the chip design. And then using reinforcement learning, we can then do this many times and use the reward signal to get better and better at placing that particular block. And so here, what you see are the white blurred areas are macros, and the green blurred areas are the standard cells or logic. And what you see on the left is a human expert design where they kind of put the memories around the edge and the green standard cells in the center, but in fairly regular patterns, like a kind of fairly rectangular style thing. And this took 6 to 8 person weeks to lay that out and had a total wire length you see there. If you use a machine learning based, reinforcement learning based placement system, what you see is it does somewhat similar things, except it is much smoother in how it sort of maps all the macros around the logic and is actually able to get to something that is a lower wire length than the human expert design, and it can do it in 24 hours instead of 6 to 8 person weeks. So I think this is one important problem to solve if we want to sort of really get to be able to produce chips more quickly and with less human effort. And we've had increasing adoption of this RL-based placement in more recent Google chip designs. So it's used in production to produce placements for multiple generations of TPU chips, as well as other non-TPU chip designs. An increasing number of blocks are used over time for the designs. The RL-based placement is used for an increasing number of blocks. The earlier versions had problems with very congested blocks, but we've been working on the RL algorithms and gotten significant improvements in the ability of it to deal with those kinds of congested blocks. And so more and more of them are now fully RL placed. And increasing improvements in the wire length reduction over time as well. So from generation to generation. And where kind of 3% is considered quite significant. And now we're sort of well above that with the more recent generations. We've actually also released this system as an open source repository. So released the distributed reinforcement learning infrastructure and the circuit environment used in the Nature paper. The repository has been adopted by a bunch of people and forked. And the Nature paper's results were independently validated and reproduced by the TensorFlow agents team. So the TensorFlow agents team had a slightly different software framework for expressing RL algorithms. And so that was used for this open source implementation. And the open source implementation is what we now use in production floor planning for our TPU designs as well. Okay, let's talk about the front end of the chip design process, which is architectural exploration. In a similar way, you can actually use reinforcement learning to explore a bunch of interesting choices in high-level architecture decisions in order to sort of accelerate the design process. And, often in hardware design, the search space is quite large, 10 to the 13th search space. and how workloads actually get mapped onto this hypothetical hardware by compilers or other software, that actually dramatically expands the search space. And you really want to consider that as well, because that dramatically affects the efficiency of how how well code would actually run in a real system that used this architecture with a compiler that made the right decisions for the architectural choices that were made. And so you can explore a bunch of different kinds of dimensions of the architectural design, like how much, what the systolic array sizes should be, how much bandwidth it should have to memory, and what the L2 sizes and L1 sizes should be. This is how you get to a large design space. And one thing you can do that's kind of interesting is often as a computer architect, you're trying to design a chip for a whole set of workloads. And you're trying to make, some balanced decision that is pretty good for this sort of representative panel of workloads. One thing you can do on the left here, everything up to here, is if you, all the green things are if you specialize for that particular model. So if you want a chip that can run this model really well, you can actually get, quite significant speed ups, 2x to 6x, better performance than a less specialized baseline architecture. And so that's kind of promising, because sometimes you do have workloads where you really care deeply about this particular workload. In the paper, there's actually where you take a bundle of these workloads, because maybe you care about these three things and you want a chip that's really good at these three things, not just one of them. And that actually works pretty well as well. Okay, systems for learning. Let's talk about efficient and scaled training and inference. So one of the things we've been doing more recently, and I'm one of the co-TLs along with Oriol Vinyals of the overall Gemini project, which is a pretty large machine learning research and infrastructure effort to train really good models, is how do we train really high quality multimodal models at scale? And so the Gemini project was formed in February 2023. We have lots of collaborators from across Google DeepMind, Google Research, and the rest of Google. And then we had an initial 1.0 public release in December 2023, and then a 1.5 release in February, 2 months later. And there's a fully detailed archive tech report there about the 1.0 family, and there's a subsequent one about the 1.5. So one of the things we wanted to do was to make these models multimodal from the start. So not just deal with inputs in the form of text or code, but deal with things like audio signals or images or videos as a sequence of frames, both on the input side and on the output side. Aspirationally, on the output side, we decided in the first version we would just bite off image generation and text generation and not worry too much about video generation, although we can kind of hook the early models up to a video generation system, interfacing it with a text-based API. But eventually we'll sort of work on incorporating more modalities directly in the end-to-end training. But this is kind of the structure of the 1.0 and 1.5 models, is we wanted to be able to deal with lots of different modalities, and that's important, as I'll show you. In Gemini 1.5 Pro, which we released in February and talked about as a bunch of updates a couple days ago at Google I/O, 2 days ago, one of the things we introduced was a very long context window. So when you have these models, you can feed in some amount of data and then ask the model to take that data into account and then do something like, can you please take this paper and produce a nice summary, or extract all the information from the benchmark tables and present it to me in one form, or take these 3 papers and do something with it. And so having a long context window is actually quite useful because the information in the context window is very clear to the model. It's sort of got the exact contents available to it, and it can actually directly attribute things to it, or, directly extract information that's interesting. And that context window can include not just text, but also multimodal representations of things like videos or audio. And one of the things we wanted to show was that the context window worked so that you could actually, pay attention to any part of your context window. And that's what these graphs show. I'm not going to go into detail, but the tech report has, a lot of details on this. Essentially, green means if you hid something in the context window in some other unrelated document, and then you asked it, what's the secret number that I hid, then it can actually retrieve it from anywhere in the context window, no matter where you put it, for both text, as well as we made a variant of those needle in the haystack tests for audio and for video, and it was actually able to do quite well on all those modalities. So one of the nice things is when you have this context window and it's multimodal, you can actually do pretty interesting things. Like you can take a video as just the frames of the video and the audio track and say, can you please summarize this for me? And it will actually just use that content and produce a textual-based summary of that. It can actually take in an entire code base of, not just a single file, but, maybe 50,000, 100,000 lines of code. And in this case, this user took an entire code base plus all of the issue reports on GitHub and then said, can you please analyze what are the issues and which ones seem most important to fix? And then can you implement a fix for the most important one? And so this issue 980 on finish was called twice. And the model was actually able to suggest a fix, which is, you keep a flag about whether you've called on finish yet or not. And if it's already set, then don't call it again, right? Sort of the straightforward thing, but it can actually automatically implement that fix with maybe limited human sort of oversight of that. So that's pretty important. If you're dealing with a large code base and you want to, ask questions of it, maybe it's an unfamiliar code base to you, or maybe you want to automate some aspects of bug fixing or feature introduction, these models can actually do it, which is pretty cool. If you haven't played with these models, you should. Here's another example that's kind of a new way of thinking about how do you get information into a structured form. So this person just took a 7-second video of their bookshelf. And they said, gee, I'd really like all the book titles and authors in JSON. So that works, right? Which is pretty nice, right? Like it's not something you would necessarily think of doing as unless you knew this worked. But now that you know this worked, you can probably imagine other use cases where you'd want to do something like that. I saw another one of someone wanting all their tweets and replies they'd posted from their account. And so they took a video of them going into their Twitter account and just scrolling up and down in their profile. And it turned that into JSON for them. Okay, so training these models actually involves fairly large amounts of computation over fairly large training data sets. And at large scale, failures become more common because you're using more hardware simultaneously. And so first, you want to minimize failures. Obviously, that would be good. But also, once you get to a certain scale, failures are going to happen. And you want to then also focus on minimizing the time to recover. And so Gemini uses rapid recovery from other data parallel copies of the model state. So often the way you implement recovery is you periodically checkpoint your model state to disk or to some distributed file system. When something dies, you take all the jobs down, you bring them all back up, you recover from the last checkpoint, which might be 100 steps ago, and then you sort of continue training from there. And as your scale gets larger and larger, either you decrease your checkpointing interval because failures are more common, or you don't, in which case you lose a lot more time and a lot more resources every time you have a failure, because actually going back 100 steps when each step is, tens of seconds is actually pretty painful. So we actually have many data parallel copies of the model state in many different TPU chips. And so we can actually reduce the recovery to a few seconds because we can just recover from the in-memory copy that we already have in some other part of the system recover in seconds without actually restarting any jobs in our distributed job scheduling system. And so that meant that we had an earlier model called Palm where we were getting 85% good put, where good put is the percentage of time that the model training is actually making forward progress and doing useful work. And we're actually able to increase that to 97% with this, a focus on recovery time, even though the Gemini 1.0 Ultra training scale was much, much larger than the Palm training scale. Now, one of the things we use in our Gemini training setup is the infrastructure system called Pathways, which we actually published a paper about in this conference 2 years ago. And the Palm language model also used Pathways. One of the nice things Pathways provides is a flexible mapping of these components, which you can think of as, I have some ML computation that I know needs to use 64 chips, but I don't care exactly which 64 chips. And so Pathways then provides a level of indirection of what the user wants, which is I need these 10 64 chip pieces to run somewhere, and what the actual resources the system has available. So there's a Pathways resource manager that makes decisions about, well, I'm going to run these 64 chip blob here. I'm going to run this one here. If something goes down, it makes a decision to move where the home of that 64 chip thing is to some other resources that are available. And you can dynamically add or remove resources to a running system. It also manages communication across multiple kinds of different network transports. And it will use the most efficient network transport to communicate between place A and place B, depending on what the actual mapping of those components is. So I have a picture of this. So in a building, you might have a bunch of different TPU pods. And within a TPU pod, you would use the ICI network in each pod, which is essentially really high-speed network connections between adjacent chips in multiple different dimensions. So either a 2D or a 3D mesh style thing within the pod. And that's much higher speed than the data center network. But then when you need to cross a pod boundary, you need to use the data center network and you have less bandwidth. But Pathways kind of manages that for you. So you can kind of seamlessly just think about as an ML developer, great, I just have this big computation and I want it to run, please. I don't really care about pod boundaries or anything. And then let Pathways deal with that. And when you cross a building boundary, say, because you need more pods, then you now are going to use an even more congested network. But that's kind of also seamless. You might even cross wide area networks and use TPU pods in other buildings in order to sort of assemble a larger collection of computational resources to train things at very large scale. And one of the nice things is we have an implementation, a sort of a client library of JAX talking to a pathway system. And so with that, then we can drive the entire training process from a single Python process on one host, which is pretty nice because these might be, tens of thousands of chips in many pods in many different regions. And, we can actually make that fairly convenient for the machine learning researcher or developer. And that also works at smaller scales. You can have a single Python process that talks to 512 chips, and it just kind of naturally looks like a single 512 chip thing. Okay, silent data corruption, or SDCs. If you hang around during the time we're training our large jobs, you sometimes hear chatter about SDCs and various things. So despite best efforts, given the scale of these ML systems and the size of these training jobs and the fact that they run for, potentially many months, hardware errors can occur. And sometimes these incorrect computations from one buggy chip can actually spread because of the way the training algorithms work. Often you accumulate gradients on multiple chips, you add them all together, and then you propagate them into all the other chips in the system. And then all of a sudden, if one of the chips has decided to flip one of the exponent bits in one of your floating point values to 10 to the 30th or something, then your gradient of 10 to the 30th spreads to all the other chips in the system. And the model parameters now are heavily infected by this one bit error that propagated from one rogue chip that you really want to hunt down and make sure it never enters your training job again. And so, there's been some observations of this in other kinds of hardware, like CPUs, like cores that don't count was a nice Google paper by some authors at Google. And these systems non-deterministically produce incorrect results and often do it silently. It's challenging when you're running independent computations. So if you have a 1,000 machine system where those are just replicas of some system, if that happens, and you're handling many different user requests on those 1,000 different things, it's not great if one of them is flaky and like produces incorrect results, but it generally won't infect the other 999 replicas. But in machine learning training jobs, it will. And so you really care about how do you identify and quickly get rid of machines that are having these non-deterministic errors. And so often the way you spot these is there's some anomaly in some higher level machine learning metrics you're tracking. Like maybe you're tracking the norm of the gradients over steps. And what you see is sometimes there's a big spike in your gradient norm. And you're like, oh, that seems bad. That could be due to corruption in the hardware. It could just be like some data example actually really produces a large gradient based on the current state of the model, and it's not actually an error. And often you don't necessarily know which. For example, here's an anomaly, but there's not actually an SDC. It's just a particular pattern of the data that causes a large gradient spike. And then you can have the third case, which is there's an SDC, but there's no anomaly. Like maybe it flipped one of the low bits in some floating point number instead of the exponent bit. And you can actually replay steps. And one of the ways, if your system is really carefully engineered to be fully deterministic, even in like the exact order it reads input examples in every batch and the exact way it does reductions across different chips, then if you replay, you should get the same answer from the same input data in the same step. But if you replay and you get a different answer, that's an indication there's something funny in the hardware somewhere. And you can then do triangulation techniques to try to narrow down like, oh, well, it seems like it came from this particular, chip on this particular pod. And so what you do then is you then have a suspicion that something on this chip is not so great. One of the really nice things about the TPU v4 system is that it has racks of 64 chips with 16 hosts. And then there's an optically reconfigurable network that connects multiple racks together. And so you can kind of, at a conceptual level, say, I'd really like a 8 by 8 by 16 grid of chips, or 3D mesh of chips. And then if one of those chips fails, you can actually swap in a rack in the other aisle in the data center and substitute it into your 8 by 8 by 16 grid of chips and just continue running, even though that machine is not physically linked, because every rack connects to a central optical switch, which is reconfigurable, and you can make it appear as though any pair of racks is adjacent. And this is pretty important for us so that we can then swap out this rack and put in a new rack. So think of each of these rectangles as maybe representing a rack, and we've identified a defective machine. One of the things we do in the background for spares that are not part of the main training job, in green, we run some sort of code that sort of tries to exercise the machines and produce SDCs if it can. And then we can sort of be fairly assured that the machines in there are good ones and are not actually generating SDCs, even though they're not part of the main training job. And then when that happens, we can then swap out the rack that did have a chip that was exhibiting SDCs and put in this green one that we are reasonably confident will not have buggy hardware in it because we've been running checking on it in the background, and then continue on our merry way. Okay, faster inference is also a really important thing. Making inference lower cost, but also lowering the latency of inference for models of all different scales really broadens the impact that these models can have. You'd like to run your absolute highest quality, largest model for everything, but you typically can't quite afford to do that for every request or every setting in which you might want to deploy this, because sometimes for one thing, sometimes you might want to run on a phone and your model doesn't fit. But other times, maybe you have a much higher request volume and you can only afford to use a sort of medium scale model and not the largest one. So how can we actually bring the best quality models for all these different sort of size considerations and compute resource considerations to more users more quickly? So there's a bunch of inference cost reduction techniques. One is there's this great paper, also known as the chinchilla scaling laws, but it has a more bland and generic title, Training Compute Optimal Large Language Models, which helps you make decisions about how big your model should be in terms of number of parameters based on the amount of training data you have and the amount of compute you want to devote to it. Now, one problem with that paper, though, is that it really says what I care about is achieving the best training accuracy on that model. And it makes no assumptions about how often that model is going to be used for inference. So if you start to think about, well, I'm going to train this model and I want it to be really accurate, but I'm going to do 1 billion inferences on it, or 10 billion inferences, that should affect that decision, right? If you are going to do 10 billion inferences on it, you might want a slightly smaller scale model that is maybe not exactly optimal to achieve the best accuracy, but will actually achieve the best sort of accuracy for your users for the 10 billion inferences, because you've backed off a little bit on the scale of model you're training, and now you can bring that to more people. So this is an important consideration. I don't think we have the end answer in this, but it's definitely something to think about if you're training these models. There's also approaches where you can produce higher quality, smaller models via overtraining. So overtraining means compared to the chinchilla optimal scaling laws, you can instead back off and then train for longer and make more passes over the training data than predicted by this training compute optimal scaling law in order to make a higher quality but smaller scale model. It won't be compute optimal, but it will be higher quality and it will also be smaller, which is good for inference. You can also use techniques like distillation to distill the capabilities of these large models into smaller, lighter weight models. So think of the large model you have that you maybe can't afford to run on every user request, but maybe you can afford to use it as a teacher when you're training a smaller model. And that teacher actually knows a lot more than just the raw data. And so actually using the rich signal of the model's predictions plus the raw training data actually enables you to get a much higher quality model trained that maybe has many fewer parameters than if you just train on the raw data alone and don't use distillation. And this technique is pretty widely used. You can make your model sparse. So activate a small portion of a larger model at inference time. One of the things you might want is a very large capacity model so that it can remember lots of stuff from your training data, but where you only activate 5% or 10% of the model at any particular inference, and you pick the right 5 or 10%. And there's a whole line of literature about how do you activate different pieces of it? How do you learn the routing function? What is the best way to learn the routing function that chooses, which of, say, 16 different experts to activate for a particular example? And that is a pretty active area of research. I think it's a really good direction. The Gemini 1.5 model is actually a mixture of experts model, building on work that we've been doing for many years at Google. All right, I'll talk about one more thing, which is speculative decoding. So speculative decoding really enables faster decoding from autoregressive models, 2 to 3x in typical scenarios. And the one nice thing about it is it changes only the decoding algorithm. There's no architectural changes. You have your model already trained. You can apply speculative decoding post hoc in order to get a nice inference speed up. And there's no trade-off. It's guaranteed to produce the identical output distribution as if you use the large model. So the observation is decoding from very large transformer models is actually memory bound, particularly when you're doing the decoding step, because you're producing one token based on the context you've already seen. And in order to then produce the next token, you have to know what the token before that was. And so that means you need to do one pass of inference through the model in order to generate that first token. And then you come back again and you're like, okay, great. Now I have 1,001 tokens in my context window. Now I can generate the 1,002nd context token by making another inference pass through the whole model. And the problem is one of the dimensions of all the tensors you're dealing with in the model tends to be very skinny. It's like typically just one in order to actually produce this single token. And you'd really like that to be a little bit larger because you're paying the cost of bringing all the parameters from HBM into the processing cores of the accelerator, into the matrix multiply units typically, in order to do this single token. It's actually almost as efficient to do a group of 4 tokens at a time, if you could do that. So that's what speculative decoding actually relies on. And I have a nice animation, which will make this much clearer. So the idea is you're going to have a fast drafting model, which could be a small model, could be a heuristic, and that's going to quickly generate several tokens in sequence, the next 4 tokens or the next 8 tokens for what you want to produce as output. And then the target model, the big one, is going to just check these in parallel, all the 4 or the 8, and using the spare compute. And then it's going to essentially validate that, oh yeah, I did want, the first 5 of these 8 tokens. And so then that's going to enable the model to generate those 5 with a single pass through the large model to validate the 8 tokens. And it says, and then some computation to say, oh yeah, these 5 look good. And so this is kind of the animation. The large, slower model on the top there is generating 1 token at a time, and it's pretty slow. The bottom animation is really got a faster drafting model at the bottom that is much smaller and lighter weight. I will go back and do it one more time. Oh, maybe I can't. There I can. Great. Okay. So you see the drafter is generating, 4 or 8 tokens at a time. And then the larger model is seeing what prefix of that it agrees with. And when it agrees, it advances by multiple tokens at a time and then says, great, I'm now happy. I now have generated 3 tokens with 1 pass through my large model. So this is a pretty effective technique. It also can reduce latency pretty substantially because now you're generating 3 or 4 tokens per pass through the large model rather than just 1. Okay. So I'm going to wrap up. I think it's really one message I want to get is scaling and performance improvements of ML systems is really critical to these continued advances that you're seeing in the capabilities of these models. The more we can make training systems and inference systems more efficient, the more we'll be able to train more capable models, and the more we'll be able to deploy those capable models in more places with lower inference costs, lower energy costs. That's why things like, more automated chip design can also be important if we have particular model settings we care about. Being able to sort of really build hardware efficiently, have a rapid design cycle in order to do that is also important. Although the timescales for that are higher than purely software-oriented changes. But I think this is a super interesting area. There's lots and lots of work to do. And in conclusion, I think ML for systems is having pretty dramatic effects across many areas of computer systems. I showed you examples of ASIC chip design, compilers. I didn't show you storage systems, but things like learned indices are quite interesting. General learning plus handwritten code combination like smart choices enables you to actually put learned choices in the middle of traditional systems. Like you just want a few parameter neural net here instead of a if statement, and that enables you to do that. And then systems for ML is an area that continues to evolve pretty rapidly. Training scales continue to increase. There's a lot of distributed systems approaches that are going to be brought to bear on this approach. And inference demands continue to grow as these systems are deployed in more and more places. And that's all I have. Thank you very much. Oh, and thanks.
Okay, I expect there'll be a lot of questions, so why don't we line up? Anybody who has questions, we'll see how many we can get through in around 10 minutes or so.
Thanks for the very inspiring talk, Jeff. So I have a question about, I've seen you have shown Gemini has shown very good performance for long context windows, and you can do amazing things with processing videos or very large documents. And natural next step is thinking about how can we enable very long generate output like in multimodal? So, for example, you can generate the entire, say, document or entire YouTube video or entire GitHub repo just by itself. What do you think will be the key challenges to enable these capabilities in terms of both the system and algorithm challenges?
Yeah, I mean, I think what you're seeing is there's a lot of progress in, fields like video generation or audio generation. And how do you build kind of outputs that are, interesting and steerable by the user? Like you want to be able to generate a video of a school bus with a unicorn chasing it, but you want it to be also chased by your dog. And so then you have an image of your dog. How do you make a video that represents that? And, if you don't like the particular choices that were made, but you like some of them, how do you then interactively sort of interact with the video generation system to change some aspects, but not others? Maybe you want pine trees instead of oak trees, but everything else is good. So there's lots of interesting high-level UI and modeling challenges there. On the generation side, though, I think the systems challenges are pretty similar to the ones you might see for long input context, because really you want to be able to make self-consistent videos that are long. And that means you need to be able to look at what you've generated so far, or look at all the things you've generated, and then kind of do passes over that data in order to sort of make sure that, and make adjustments in the generated pixels or whatever, in order to make sure that it looks sort of reasonable and is consistent across it. And that's not that dissimilar from the input attention mechanisms.
Great, thanks a lot.
Thank you, Jeff. Great talk as usual. I have a quick question on the source of entropy that you're detecting during those SDCs. It's a source of entropy to some extent, the same way that you have those chips fail at a particular with a particular entropy. If you overclock them or if you give them lower voltage, could you actually exploit that source of entropy in a way that we exploited that source of entropy for dropout, for example, to regularize those models or to be able to train those very large systems with the lower voltage, lower power consumption, instead of getting rid of those failing TPUs or failing racks? Yeah,
I mean, I think you're right that there are a bunch of machine learning techniques that involve, say, introducing noise explicitly, like things like dropout as a good example, where you sort of randomly zero out some of your values and then you train, and that actually makes the model more regularized. I think the tricky thing about SDCs is if they were all failing towards zero, that would be nice, but they don't. And you typically don't drop out by introducing ones in the high exponent bits of your floating point numbers, which is what SDCs can do. And so I think it's a bit different than sort of the kind of classic kind of entropy you want to introduce through machine learning training methods, which is indeed a very good thing. I think there is an interesting direction of how could you build more efficient hardware that maybe is not completely precise every time, but tends to fail towards zero, right? If you could do that, that might be interesting. It's like maybe you could pack circuits more tightly together, and that would introduce some noise in the thing that normally, if you're trying to design a completely, reproducible system with errors in 10 to the minus 12 rates, then you might not do that. But if you're willing to say, yeah, errors in the 10 to the minus 6th are okay, as long as my errors tend to go towards zero, that might be an interesting design direction for how do you build more efficient systems, because maybe you can violate some design rules of your fab partner.
Yeah, there was some research on the sloppy arithmetic for hardware. Maybe we can get back to it or change the architecture to be robust to those high exponent bit flips. Thank you very much.
Yep.
Hi, Jeff. Thanks for the nice presentation. I have a question about something you didn't talk about, which is the data quality. So for long contested learning, learning from human preferences, data quality is one of the most important factors. I'm curious, from your point of view, and also for a lot of people here doing MLSys space, what are the interesting research questions for data quality and then just data in general?
Yeah, I didn't talk about it because this was a sort of more systems-oriented talk, but it's super important. In the Gemini team, we have a lot of people focused on, how do we identify high-quality data? How do we develop algorithms that can, automatically identify the relative quality of this data source or this data example versus that one? I think that's a pretty interesting, research direction. We have a bunch of good solutions for it now, but that's by no means the end-all solutions. I think things like automating the learning of a curriculum are pretty interesting. Like you obviously, if you're training a large model, it probably doesn't make sense to just mix your data together randomly and start training on a mix of C-spot run and astrophysics papers. You might like to do C-spot run more emphasized in the beginning of your training and then astrophysics more in the end. And we have some manual curation of things that do that, but we don't really have a great answer for how do you fully automate that, because it does feel like you should be able to identify that. And part of it is the real crux of the problem is, for this example, what will be the quality improvement I expect to get from my model by training on this example versus that one at this point in training, right? And if you could do that and answer that question cheaply, that would be awesome.
Thanks.
So thanks, Jeff, for the very interesting talk and also the very impressive work you have done in the Google. So I'm Guohao from Shanghai Jiaotong University, China, and I have two questions. The first one is about the hardware, because you mentioned that machine learning helps a lot for the system and hardware design. So in your opinion, what is the most important feature for the next generation hardware in both data center and also the embedded system? And also the next problem is about the scaling law, because you mentioned that we do need a lot of parameters and also the beta lesson from the rich Saturn. But that scaling is not that easy because of the data and also the computing power you have also mentioned. So in your opinion, will the scale of the next generation model still to grow or scale, or it may converge to a certain size in the next few years?
Yeah, I mean, I think it's a hard set of questions to answer because there's many complicated trade-offs in all of these different decisions. I think one thing you want is more high-quality training data. I think there exists in the world a lot more high-quality training data than we're currently training on. So that implies you want to make your models bigger in order to sort of take advantage of, presumably better data that you can find for future models and larger sources of data. I think sparsity is an important tool, because if you have a very large data set, you want a model with enough capacity to absorb that large training data, but you would also like the model to be somewhat efficient at inference time. And greater degrees of sparsity seem like one interesting lever for that. Another trend is quantization, particularly for serving. People are already using 8-bit quantization quite aggressively. 4-bit quantization seems like it's working. There's a bunch of nice papers in this conference about 1-bit or even sub 1-bit quantization that are kind of on the leading edge, but seem like a trend that you want to consider for future models or future hardware designs. It seems as though we might be able to get by with a lot less precision than we are currently in some of our some hardware. That was sort of the original observation of the TPU v1, is we didn't need floating point, we just wanted int8. And I think the same lesson is playing out in training and at lower bit precisions as the whole field has progressed in this space. So,
so you mentioned the sparsity. So, sorry.
Thanks. Hi, Jeff. Great talk. So my question is in regards to one of your slides. You quickly went over a mixture of experts. So my question is about, is there an upper bound to the quantity of mixture of experts? And if not, how do we identify the optimal quantity?
Yeah. I think a lot of the models today are using sparsity, but in fairly regular ways. Like all the experts are the same size. There aren't that many of them, maybe 16, maybe 64. And then they kind of merge right back together. And then you do another bank of experts a layer above or 2 layers above or whatever. It feels like that's a pretty limited variant of the full design space of sparsity. Like one thing in particular is I think we want to devote more computation to more complex questions or more complex contexts. And you see this both at the individual token level, like some tokens are much harder to predict than others, but you also see it at the overall example level. Like if I give it an image and ask what's in this image, if it's a simple image, I might like to have, if it's a very complex image, I might like to have 100 times as much compute used for that problem than a very simple one. And so I think sparsity could be a way that we can get variable amounts of compute where maybe you make the experts all very different sizes. And now you call on the really cheap ones most of the time, but then occasionally you invoke a 100x as expensive expert, and you try to balance the computational costs in the right way to improve the overall accuracy of the model. And maybe you don't merge right back together. Maybe you have kind of more like a more complex graph structure of this. And that means you care a lot about, maybe asynchronous methods, because maybe now you have different paths that take different amounts of time for training these systems. So I think there's a whole range of things one might care about. I gave a talk at a sparsity workshop that I think is online that has a 20 to 30 slide riff on some of these issues.
Awesome.
Yeah, hi. I was wondering, what are your thoughts on whether transformer architecture is here to stay now, or whether you see bottlenecks that, maybe video generation or things like that maybe other architectures could emerge?
Yeah, I think there's a bunch of design choices in the transformer that I think you might want to investigate, right? Like the autoregressive one token at a time decoding, that's one approach. There's other approaches like text diffusion models where you generate, 1,000 tokens and then you run multiple passes of denoising to fix them up. And you only run maybe 30 passes total to do that. So that's kind of an interesting approach to how do you actually generate output from these models. They're commonly used in image generation or video generation, but people are starting to explore their use in text models. So that's kind of an interesting direction. I think the attention mechanism, the straightforward quadratic attention mechanism in the original transformer paper, there's a whole litany of literature of trying to make that subquadratic, because quadratic sucks. But I think often what you see is that, yes, you can get subquadratic, but you pay some quality hit. And, the trade-offs there are not totally straightforward. If someone had an n log n attention mechanism that has no quality loss, yeah, that sounds great. But I don't think we have that quite yet. So.
Yeah, thanks, Jeff, for the great talk. So, Jianming from Georgia Tech/MIT. I have two questions in total. First is, seems that currently TPU is a major stream for AI. And I wonder how is TPU being envisioned to support general purpose vectorized and matrix multiplication, these for other applications. And if that was still in the timeline, what will be the tool that for external programmer from academia or industry to do that? And second question is, you mentioned about SDC.
To access TPUs?
Yes, and how to program this to support general purpose matrix and vector workloads, this kind of thing.
So let me do the first one, which is you already can use TPUs today. We have a cloud TPU program. We have many customers. We have some academic research efforts where we can give TPU resources for academic projects. The TPU Research Cloud, you can look for that. And people just use those TPUs just as we use them internally. And they can already support, non-machine learning computations through JAX or PyTorch. And basically, you can get auto differentiation, which is very useful for other non-machine learning computations, or you can just express matrix and vector computations that you want to do in JAX.
Thanks. The second question regarding the SDC, you just mentioned that you have a great tool to detect what is the bit flipping and what is the costing for that. When asked, what do you envision as the future mitigation for it? Will it come from the software side or hardware side?
Yeah, I think there's a lot of different solutions. So one is, making machine learning algorithms that are more robust to this sort of thing, and maybe throw away outliers in your gradients rather than just naively adding them together. Maybe the hardware itself can be more robust to that. So future designs, you could include more redundancy and maybe have more internal checking in the actual hardware circuitry to identify it has something bad happened. This is sort of what happens with ECC memory and you can actually correct certain kinds of errors in that. And maybe there's the analogous things you can do in the actual computation units of these chips. So there's a whole range of possible solutions. I think the whole every level will get better, but at the moment, as you try to scale things up, things are getting better, but you're also scaling things up, which makes things worse. So it's a fight.
Yep. Thanks so much.
Hi, thanks for the interesting talk. I have a question about the limitations of ML for systems. What do you think the main limitations are, and how do you decide whether to use ML or human-based understanding to tackle some particular tuning problem?
I will. I think this is the entire topic of the bitter lesson thing. I think the lesson is every time you try to use human understanding and you actually have the ability to use enough computation and enough learning, generally the learning approach works better. Now that you can't use it everywhere, because I think sometimes human intuition is very close to the answer a learned system would give. But there's a lot of cases where learning, even in non-intuitive kind of settings, would be much better. Like imagine you're trying to figure out how many replicas on disk to make in a distributed file system, right? You would never probably put in handwritten heuristics that say if the directory name above it is /tmp, then it's probably not going to live very long. And so I can now make fewer copies of the data. But a learning system would be able to learn that and say, oh, well, I don't need to make as many copies of this because probably that data is not going to live very long. And I think that's what we should do, is open our eyes to being able to learn these kinds of things in a lot of our systems, and they'll be more efficient, they'll perform better, they'll do better, make better decisions.
Hi, thanks for the great talk. I had a question about the ML for systems portion. So a lot of the examples you went over were kind of like low level on the hardware software stack. I work on ML for systems group at Netflix, and I think a lot of the projects that we're kind of steered towards are kind of like higher level. So things like task scheduling, config optimization, things like that. Which can make sense because it's easier to integrate, faster release cycle, and other benefits. But I'm curious in your experience where you've seen the most impact in applying ML for systems.
Yeah, I mean, I guess the YouTube caching example is a pretty high level one. Yeah. That's like a software managed cache. So that's maybe a good example of a high impact one that is not like in the guts of your malloc implementation. Yeah. The learned index paper that I'm a co-author on is an interesting one that's pretty high level. I think, basically learning in a lot of sort of scheduling systems makes a lot of sense, because often the decisions of what to run next are complex, and you have a lot of information available at the scheduler that it typically doesn't make use of at all. And so that seems like a nice high level thing, as you point out, for test scheduling, or, which job should I run next or whatever. It makes a lot of sense.
Great. Thank you.
Yeah, thank you.
Cut off the question. So this will be the last one.
Okay.
Oh, thanks for your talk. And which model evaluations do you trust most in your engineering work?
I didn't talk about this topic. I kind of like data because this is a systems talk, but I'm happy to talk about it. Evals of machine learning models is a super complicated space. There's lots and lots of academic evals. If you look at our Gemini tech reports, we did 32 different eval suites for the 1.0 and added a bunch more on the 1.5. And we have a whole bunch of internal evals that we don't publish about because they're more product focused evaluations, and people can't run them anyway. So the kinds of evals we believe in the most are the ones that we know our model has not seen anything related to that in the training data. And we do as good a job as we can of eliminating test or train or evaluation data from these benchmarks from our general training data. But it's still the case that people will post like a random GitHub repository of MMLU benchmark data and results from their kind of crummy model on the test set, transformed in some way that it doesn't look like an exact duplicate of the MMLU test set, say. And then your really awesome model is training on someone's kind of crummy model output that is all wrong answers. And that makes you sad. So I think the most reliable benchmarks are ones where you know nothing is leaked. So we have a bunch of internal coding benchmarks or a bunch of internal things in the spirit of some of the academic benchmarks, but with different questions. It's amazing how much some of even the very popular academic benchmarks come from a handful of websites, even though they were generated by humans. It looks like some of the humans just looked at some websites in order to, come up with the questions. And if you include those websites or not in your training, then you get very different quality. So it's a complex question. I think ultimately what people care about is, does the model do the things they are trying to get it to do? So there's also nice online systems like MLSys that people are sort of exercising the model for things they care about and can rate A or B, which one's better. And those tend to be, reasonably believable, although those can be gamed a little as well. So complex area. Happy to have our evals people talk at length about it.
Okay, with that, let's thank Jeff one more time.